Hello, my name is Brad Strebig, and today I want to talk about chemical reactivity and activity effects for aqueous solutions. This will lead us into modeling aqueous solutions and how to differentiate between accurate models, ideal models, and non-ideal models. Chemical reactivity refers to the overall tendency for a particular chemical to participate in reaction. This should be straightforward enough. It incorporates such factors as the concentration of each species. The more of something there is, the more it is likely to bump into something that will react with. So generally, the greater the concentration, the more reactive something is. Again, fairly intuitive. The greater the temperature, the more excited the atoms, typically again, the more likely we are to have a reaction occur. There may be other system elements that play a part too, and this includes the concentration of other species that are dissolved in solution. So the reactivity term characterizes the instability of a system. In very dilute solutions, ions behave independently of one another, and we actually have what's called an ideal solution. So if we have a compound A and it wants to react with a compound B, there's nothing preventing them from coming together and having a reaction. These compounds can move freely in solution and form a different compound than the compounds we started with, compound AB. The ionic strength and activity are related. As we have a higher ionic strength, we have more and more dissolved ions in solution. Think back to our example in Death Valley, where we had a water body where water constantly comes in over many years, coming into this body of water, the sun evaporating the water in this hot, arid region, and increasing the concentration of dissolved ions in solution. All those ions create an ionic soup that gives alignment and structure to the water, or the fluid in this case, or solution. And all these ions create a shielding effect, or kind of hide other ions in solution, preventing or reducing the effective concentration of ions with the possibility of reaction. The lower reactivity is accounted for in our mathematical estimates by different estimates based on ionic strength, and we use a factor called an activity coefficient to account for this reduced activity. So activity and concentration are going to be related in a system. In an ideal system, the molar free energy depends only on the mole fraction of the solution. In dilute solutions that are ideal, most of these interactions are caused by electrostatic forces. But in non-ideal solutions, especially when the concentration of dissolved compounds is large, these interactions can lead to variations in electrical potential of the solution, decreasing the total energy of the system and decreasing the chance of a reaction to occur. So we account for this by using the activity instead of concentration of compounds in solution to measure how reactive that solution will be. Let me say that one more time. We are going to use a term called activity to measure how reactive things will be in a non-ideal solution. So here we have an example of a non-ideal solution where there are lots of ions in solution. Because of that, the electrostatic interactions increase, and compounds A and B have to take a longer path to come into contact with one another. We may have paths that move around and create shielding. Eventually these compounds can come together, but you can see that the other ions interfere with the formation of AB. We call that interference a change in the activity of the solution, and we utilize the activity coefficient to take this into account. So the activity is defined as the effective or apparent concentration of how compounds will react in a solution compared to a dilute or an ideal solution. In most freshwater environmental applications, the activity and concentration are used interchangeably. However, in seawater, briny groundwaters, Areas where we have high concentrations of compounds in industrial wastewaters and other concentrated waste streams and estuaries, we need to account for these effects because they'll change the chemistry and reactivity of the solution. The activity is designated in chemistry by these curlicue brackets, whereas concentration in moles per liter is designated by the square brackets. So both activity and concentration will have units of moles per liter, or we can use normality, but we'll change the way we note those with the curlicue brackets or the square brackets. We have to make some assumptions because activity is really a comparison between the ideal state and the non-ideal state. So it's a relatively arbitrary measure. So we need to create some standard state conditions. So we're going to define an activity equal to 1 under standard state. Our reference state then is going to be at 25 degrees Celsius and 1 bar or atmospheric pressure. The standard state is going to be a function of the standard concentration, a standard pressure 1 bar, standard temperature 25 degrees, and standard composition of compounds. Here we see the temperature and pressure remain the same, but depending upon the state, will determine how we define our pure or unit activity. For a solid, we assume that the concentration is purely that solid, and we define that activity as unity. Likely, for a pure liquid, we define that activity equal to 1, and for a pure gas, we define that equal to 1, and for a pure solute, we define that as a 1 molar compound. We'll come back with some clarity on this in just a moment. We're also going to relate a term called the activity coefficient to account for the effects of all those ions in solution. Previously, we measured those ions in solution with the ionic strength. So the activity coefficient relates the activity to the concentration of the compound. And it depends largely upon the ionic strength of the solution, and the ionic strength is a measure of those interaction forces and can be measured or estimated from the measuring the ions themselves, measuring the total dissolved solids concentration, or measuring the resistivity of the solution, how electrodes move through the solution, that is. So if all the concentration of all the dissolved ions in solutions is known, then we can calculate the ionic strength from the sum of Ci times Ci squared. However, often this isn't the case, we'll need to make some assumptions based on total dissolved solids or some other empirical correlation. Once we calculate the ionic strength, we're then ready to calculate the activity coefficient. The activity coefficient is simply defined as gamma sub A for a compound A, and it's equal to the reactivity of A in the real or actual system where we have shielding effects due to ionic strength compared to that of an ideal system or our reference strength state. Simply put, this is equal to the activity coefficient is defined as the activity divided by the concentration under the standard state. There are various ways and empirical estimates to calculate the activity coefficient. For low ionic strength solutions, we can use a Debye-Huckel rate limiting law, which uses empirical coefficients for A equal to 0.51 and is a function of z squared. Again, we saw that similarly, that the charge of the ion has a great effect in the electrostatic fields that it creates around it, and the ionic strength of the solution raised to the half power. For slightly higher ionic strength solutions, those between 0.05 and 0.1 molar, we can use the extended Debye-Huckel equation. And these values for the terms are given in a table in your textbook. For even higher concentrations, possibly seawater, we can use a Davies approximation, which uses slightly different empirical parameters, but is still based on the ionic strength. In table 2.13 of your textbook, you'll see several activity correlations based on empirical measures related to potential ionic strengths and the charge for different ions. As an example, previously we measured the concentration and ionic strength in the Ganges River. We can estimate the activity effects of those ions in the Ganges based on the concentration of dissolved ions in solution. Recall that we calculated the ionic strength of the Ganges was 2.66 times 10 to the minus 3 moles per liter. Using the Debye-Huckel limiting law, which is valid for solutions with this approximate ionic strength, we can solve for the value gamma for sodium. The log of gamma for sodium, the activity coefficient for sodium, is going to equal minus 5 times z squared times the square root of the ionic strength. In this case, our z value is 1, so it's going to be minus 0.5 times the square of 1 multiplied by the square root of the ionic strength, which was 2.66 times 10 to the minus 3. That is equal to the log of our activity coefficient. When we take the inverse log of that value, we have an activity coefficient of 0.941. Note that the closer we are to 1 for the activity coefficient, the closer we are to an ideal solution, and the lower the effects of dissolved ions are in solution. So the reactivity of sodium is going to be very, very close to an ideal solution for the Ganges River water. If we look at the calcium ion in solution, and again here note in yellow that there may be some typographical errors in the subscripts in your textbook. The calcium ion has a charge of plus 2. Plugging that value in gives us a slightly different value for the log of the activity coefficient, and when we take the log, the activity coefficient for a divalent cation calcium has an activity of 0.788, or about 0.8. So it's going to react, one way of thinking about this, of 80% of an ideal solution. This is beginning to get in the border range of where these activity effects for multivalent cations could be fairly significant in subsequent calculations. For the bicarbonate ion, it has a charge of minus 1. We substitute in minus 1 for the charge in our equation for the carbonate ion, take the square of that, which becomes positive, the square root of the ionic strength, and we get a value of 0.0258. Taking the inverse log of that value gives us the same value. So notice that whether it's a positive or negative charge, since the charge is squared, we'll have the same value for the activity coefficient for all monovalent cations and all monovalent anions. Also, anything with the same charge, plus or minus, will have the same activity coefficient. Again, for monovalent ions, very little activity effects will be measurable. So notice that the charge, again, as it was in calculating the ionic strength, is going to be very important in calculating the activity effects or lack thereof. I've showed you the activity concentrations and the relationship between activity and concentration and how to calculate those effects. If we were dealing with seawater solutions or estuaries where the concentrations of dissolved ions were very high, we would need to take those activity effects into account. However, in most of this course and most of the rest of the textbook, we'll be assuming that the total dissolved solids concentration is relatively low and that the activity effects are relatively low, such that for most freshwaters we can usually consider them as if they were an ideal solution and assume that the activity is essentially equal to the concentration in solution. But as it is important to know, if you deal with the Chesapeake Bay estuary or global change in the ocean and ocean acidification, which we'll talk about in Chapter 6, we'll talk about the Chesapeake Bay in Chapter 4, we would need to take into account these activity effects to do an accurate model of what happens to chemicals in the environment, especially in saltwater or semi-saltwater waters. So in summary, we want to determine chemical species present in solution. This can sometimes be a difficult task, so we may use some empirical measures or other conventions by grouping compounds together by element or physical parameters, like estimating things by their average weight of calcium carbonate rather than determining the actual weight of each individual ion, estimating ionic strength from dissolved solids rather than actually measuring each individual ion. And sometimes these units are just by convenience or by history, as is the case with the calcium carbonate. Regardless of the complexity of these processes, the math is relatively straightforward. It's just a matter of learning some conventions, a little bit of vocabulary, and being able to apply these basic understandings and principles when they need to be applied, particularly in saltwater systems, when we have water softening issues, and when we have taste or other issues that may interfere with the ability of the water to perform the task given at hand, whether it's an industrial task or simply for drinking water. Next, we'll move on to talk about how the chemistry of the hydrogen ion has a significant impact upon environmental effects.